Here we go. And we start with these two videos, right?
Yeah.
Okay.
Hi, everyone. I'm Emily Allen, Dean of the College of Engineering, Computer Science, and Technology at Cal State LA, and I'm here to welcome you to our virtual Capstone Expo 2020. That's the Expo that's virtual, not the Capstone projects. In fact, our student teams have been working on their projects since our kickoff in August 2019. That seems like a long time ago now, as the COVID-19 pandemic has forced us into physically distant but socially cohesive modes of operation. We have over 100 project presentations to share live with you over Zoom connections. We are very proud of our excellent senior design program, as it rivals programs nationwide in meeting curricular requirements for design. Engineering design is an iterative, creative, problem-solving process in which science, mathematics, and engineering and computing principles are applied to convert resources into solutions. It has a direct and vital impact on the quality of life for all people. With these stakes in mind, our students have been working hard all year long, and especially these past few months, to finish their projects, and these presentations represent the culminating efforts for their degree programs. We deeply appreciate our project sponsors and industry liaisons, our faculty advisors, and the teams that manage and provide instruction for these capstone courses, including Mike Thorburn and Chris Bachman, John Shamma, Howard Lum, Jason Song, and Rupa Purasengi, Paul Liu, Elaine Kang, Jungsoo Lim, and Raj Pumula, as well as our staff members, Hasmeek Simon and Evelyn Lee. Now, on with the shows, and I'll see you online.
And one more video.
Play the next video.
Is this the meeting or is this?
Hi, everybody. I'm Mike Thorburn, and on behalf of the Cal State University, Los Angeles, and the College of Engineering, Computer Science, and Technology, I want to welcome you to the 2020 Engineering, Computer Science, and Technology Capstone Senior Design Expo. This year, it's a truly unique experience for us and for you, as the Expo will be done live via Zoom. Additionally, sessions will be recorded for those not able to participate in the live event. The students have all worked especially hard to make this event happen and to ensure the audience is able to participate from a safe social distance. Between mechanical engineering, electrical engineering, computer science, civil engineering, and technology, we have about 100 presentations scheduled over a period of about 2 weeks. I encourage you to participate constructively in as many as you can. Your feedback is critically important to the students. As you're watching this video, you must already know about our webpage. If you take time to go through it, you will find detail about all of the presentations and projects. Cal State LA is protecting the event from mischief by using passwords, but if you request access, we'll happily send it to you. The students have been working on their projects since August of 2019. Obviously, the COVID-19 epidemic was a huge disruption over the last month and a half, and it's been hard for everybody. I'm proud to say our Cal State LA Engineering, Computer Science, and Technology students, just as they have always done, have shown great persistence to overcome the obstacles confronting them and have made a tremendous effort to wrap up their projects and present them to you now. On behalf of the university and on behalf of these terrific students, I welcome you to Expo 2020.
Okay, so we'll start our presentation. Hello, everybody. My name is Jonathan Tahod.
I'm Jonathan Ung.
My name is Pierre.
Okay, and we were going to be presenting our project on the software implementation for the CubeSat, which was sponsored by the Aerospace Corporation. So first and foremost, I want to thank our advisors, Denny, Pablo Settecase, and Karina Martinez, as well as our advisors, Russ, Abbott, and Sue Lim. In addition to that, I want to thank Jimmy Lopez for his help with part of the project. He was one of the mechanical engineers on the CubeSat team for another part of the project.
So the problem that we're trying to solve is the increasing amount of space junk in Earth's lower orbit. So space junk is comprised of debris as well as decommissioned satellites. As of January 2019, there's over 128 million estimated bits orbiting Earth's lower orbit. The reason this could be a problem and is worth putting effort into resolving is the fact that space junk can be a potential hazard to current missions as well as missions in the future. So the solution to this would be to deorbit the space junk as well as repair wounded satellites. So here are some of our project objectives. They're that we must be able to simulate navigation in a zero gravity environment since we're trying to replicate motion in space. Also, we need to be able to navigate safely towards a target, which in this case for us, it would be a wounded satellite. So what is a CubeSat? A CubeSat is a small spacecraft. The CubeSat standard was developed by Cal Poly San Luis Obispo, and they're currently over 900 in space right now. The CubeSat is measured in 10-centimeter increments called U's. The one that we have in the slide isn't depicting the same version that we have. The one in the slide is a 1U version, and the one that we have is a 3U version. So now I'll give you guys a little broad overview of the three main systems of our project, the CubeSat, SimPlat, and ground system. The CubeSat is supposed to be smart and autonomous. You could think of it as the brains of the whole system. And CubeSat and SimPlat are meant to be independent of each other. CubeSat just uses the SimPlat to simulate 2D motion in space. The SimPlat is just a physical platform used for this. The ground system and the CubeSat are part of the same system. The ground system is the user interface. It displays the live camera feed and it has buttons to control the CubeSat. So that's just basically used for the user. And now we'll go into further detail on the CubeSat.
Hi, so here's a brief overview of the systems and how they connect with each other. So if we follow the system from the user's point of view, what the user interacts with mostly is the ground system. And from the ground system, you can input two different things. So first, you can see a display. And what the display shows is information that's given by the CubeSat. These are things like the camera and any other data that CubeSat wants to display can also be transmitted to the ground system for viewing, any kind of data at all. And from the ground system, you're also able to control the movement of CubeSat. So you can send, this would be done in like a manual mode, and you're able to actually send commands that would move it left, right, forward, diagonally, rotate, things like that. As you can see, as mentioned earlier, SimPlat is the physical movement portion of the CubeSat, and that's the part that gets commands from both CubeSat as well as ground system, if you so choose. CubeSat is isolated pretty much from user interaction. They don't really interact with CubeSat. CubeSat acts autonomously. It calculates and it retrieves data. It calculates and creates navigation commands that it sends to SimPlat to move, and then displays data. So next we'll see some sensors. These are the sensors that were given to us at the beginning of the project. So on CubeSat, we have a camera. This works like a standard camera. It gives us a video feed of what's in front of it. And there's a single one placed right in front of CubeSat, so it can see exactly in front of it. CubeSat is also loaded with a Raspberry Pi, and this acts as the brain. It computes everything, controls all the sensors, and sends back data and things like that. We're also given 4 TF mini LiDAR sensors, and what those sensors do is detects objects directly in front of that sensor. They're placed in all the cardinal directions, so we're able to see in north, south, east, and west, things like that. So here's a quick overview of each component's purpose. For the CubeSat, its purpose is to use the sensors loaded on CubeSat, which are the camera, and the LiDARs if you choose, as well as a 9-dot. And we use those sensors to get information about any targets, as well as the environment around CubeSat. Once we get that information, things like the distance from a target, the angle, a target might be, we use that information to track and locate a target. And with that information, it calculates the commands necessary to move CubeSat towards the target we're trying to reach. The next component is SimPlat. And SimPlat's main objective is to simulate 3D movement in a 2D space, a 3D space movement in particular. So if you think like a satellite in space, you know, a satellite is able to move, it's able to move freely as well as maintain its momentum. SimPlat's job is to do the same thing, but on a 2D plane. SimPlat's main purpose, or sorry, the only inputs that SimPlat receives are commands. And then once it interprets that command, produces physical movement. But other than that, it's not very intelligent. It doesn't create its own commands or things like that. On the physical SimPlat, you see there's 4 omni wheels, and the 4 omni wheels basically allow SimPlat to move on a floor or surface in any direction whatsoever, given the right commands. So that's what's special about the omni wheels. Other than that, they're just standard wheels, and it's also loaded with Raspberry Pi, and this is basically just to control the wheels as well as receive the information from the other systems. Then next we have I'm going to go a bit into depth about how SimPlat works. So as mentioned earlier, it basically just receives commands, turns those commands into motion. And it does so in a way that simulates 3D motion in space on a 2D plane. So we used a kind of like a thruster principle, and I'll go a bit into detail about that in a later slide, but just keep that in mind. And as I mentioned, it maintains its previous movement until a counter thrust is sent. So what that essentially means is that if you think about a satellite in space, if it's moving, whether from a thruster or physical movement or whatever, it'll continue moving in space without having anything done to it. And this is like a conservation of momentum. And one of the goals of this project is to simulate that movement. So then SimPlat works the same way, in that if it's moving in a certain direction, it'll maintain its movement even when no movement command is given. And in that way, we try to simulate just a conservation of momentum on a, on Earth, where conservation of momentum would be dragged down by things like gravity and things like that. So that's how we accomplish it. Moving on. So here's a overview or a flow map of how commands are sent into motion. So basically, things all start at the camera that's located on CubeSat. It's given all the sensor information, things like, so given the camera, we get camera frames, and using those frames, we locate a target, its distance, and other information about it. We use that information to create commands. And then we send those commands to SimPlat, where it interprets those commands and turns it into physical movements. So now I'm going to go a bit into the thruster system. Here, when we think of the thruster system, we try to think of it as like a satellite moving on like a plane. If we attach 8 thrusters to the satellite, we can use any combination of thrusters in order to simulate movement in space in any direction. And so here's a basic example. If we wanted to do a forward command, we would activate the forward and 5 thrusters. And what this would do is that it would move SimPlat forward, kind of like a rocket or like things like that. Activating those thrusters will move it forward. Similarly, if we wanted to move it backwards, we would do the opposite, thrusters 8 and 1. In addition to this, if it were already moving forward, then doing the backwards command would actually stop it. And so this is how we both use the conservation of momentum to our advantage. So if we sent a forward command, it would be continuously moving forward. If we wanted to stop it, we'd have to send the opposite direction. So in order to make sure we know where SimPlat, how fast SimPlat is moving. We just have to make sure we maintain our thruster usage so that we're always sending, if we're always moving forward, we send a appropriate thruster to stop it and things like that. Thruster commands are also additive. So if we wanted to do diagonal movement, we would add a left command as well as a forward command, things like that. So there's a lot of variety of uses with this thruster system. And with the added bonus of it being 8 thrusters, it's able to simulate like a byte. So we're able to send commands through a single byte, which is 8 bits, very easily with this structure. And so now John's going to talk a bit about the actual computing.
Cool. So I'm going to talk about the software that we designed for the cameras, or for the CubeSat's vision, I'm sorry. And so utilizing the camera as well as OpenCV in Python, we were able to have our software detect objects as well as to detect and track certain objects. And so what we had them tracking, or what we had our software track, was the Oroku marker. If you go to the next slide. Oroku marker. So this is what an Oroku marker is. On the left-hand side is just your basic Oroku marker. And from this, our software is able to detect X, Y, and Z changes from the Oroku marker, depending on the size of the Oroku marker that's inside its frame of reference, I'm sorry. And then going on to the next slide, this is actually how we're using, or how our software is calculating X, Y, and Z of the Oroku marker. So basically by calibrating the camera, we're able to determine the values for the X, Y, and Z coordinates inside of the frame of reference. So yeah, basically by telling how big the certain object is inside of our camera, we're able to tell how left or right the object may be, and so on and so on, as well as, you know, how far it may be from away from the camera. And so this is also known as the pinhole method. So going on to the next slide.
So moving on to the navigation software, or the autonomous mode of CubeSat, it's designed to track and follow a moving target, and accomplishes this by taking an input from OpenCV, as mentioned before, and with that input, it generates the appropriate thruster commands to send to SimPlat. So when the autonomous mode first begins, it performs an initial search. It does this by sending a clockwise rotation command to SimPlat to begin a rotational movement. While it is rotating, it's constantly checking its camera frames to see if the target is within its view. Once it recognizes that it can see the target in its camera, it will send a counterclockwise command to SimPlat in order to stop the initial rotation, and from there, it will start receiving input from OpenCV. Depending on the input it receives from OpenCV, it'll generate the appropriate thruster commands in order to reach the target. Say, for example, in a camera frame, the target was towards the left edge of the camera screen, meaning, and when this is the case, CubeSat wants to rotate itself in order to bring the target back towards its center field of vision. So in this scenario, it will send a counterclockwise command to SimPlat in order to rotate left. And it will keep rotating left until the target is closer to the center of the camera. Once the target is within the sensor, it will send a clockwise command to stop its rotation, and from there, it will issue a forward command to close the distance between itself and the target. The idea behind this logic is that CubeSat should be able to follow and track a moving target within its camera view. Here's a demo of CubeSat trying to find a stationary target. As you can see, it's not the perfect movement, but one thing I do want to point out, in our current iteration, our navigation software currently does not rotate or move at the same time. What it does is that it either rotates first, then move, or vice versa. So moving on to the ground systems. Here's a wireframe mockup of what we wanted our ground system to look like in the final version. In our current version, we are able to display the CubeSat's camera feed to the user, as well as allow the user to manually control SimPlat's movement in order to move CubeSat. So here is a screenshot of what our current manual mode looks like. There's several buttons that the user can click on to issue commands to SimPlat so that SimPlat can activate its thrusters to move CubeSat. As you can see, there's the directional movements as well as the rotational commands. And there's also a stop button that the user can click on to issue a stop command to SimPlat to stop its wheel movement. There's also a start detection track. The idea behind this button is to allow the user to switch between manual mode and an autonomous mode with an easy click of a button. However, we weren't able to implement this feature in time, so the user does not have an easy way to switch between autonomous mode and manual mode in our current issue. So in this demo, although the videos are a little bit out of sync, when the user clicks on the thruster commands on the web page, it'll issue those commands to SimPlat, and SimPlat will perform those thruster commands accordingly. It can perform the rotational commands as well as the directional commands. And as you can also see, SimPlat's movement isn't perfect here, as there were some calibration problems with one side of its wheels. One side of the wheels is unfortunately more powerful than the other wheels, so that one pair of wheels will rotate faster than the way we wanted it to.
So we had some constraints as well with the project. For one, we had to work with Raspberry Pis, and as some of you may be familiar with, Raspberry Pis are limited to power. And because we had two Raspberry Pis, one on the SimPlat and one on the CubeSat, we had to be very mindful of this. We also ended up using a lot of CPU, which caused a bit of a lag and a built-in delay that we didn't intend. For SimPlat, the OmniWheels restricted us to only being able to simulate 2D motion. And for the camera, since we're using object detection and it was done with Aruco markers, there was a bit of a constraint with how far the camera can read its target, as well as the camera approaches too close to the target, it began to have blind spots when it got too close. And throughout this year-long project, we had encountered several problems. Many of our problems had to do with the hardware. The first problem we encountered was deciding how SimPlat should move accurately so that it could replicate motion in space, and how we wanted the thrusters to be fired. We also ran into some battery issues because the power for the batteries wouldn't last that long. We had to constantly charge them, and charging took a long time as well. Another problem that Jonathan just mentioned was the calibration of the wheels. Some of the wheels rotated at different speeds than the others, so we had to try to calibrate them so they are all in sync. And lastly, we had some router issues, mainly having problems signing in at school and deciding which router to use. For future work, we recommend that you make CubeSat more intelligent by using machine learning. Machine learning can be implemented to make the navigation a more intelligent navigation algorithm, as well as making the camera vision more intelligent for object detection. As for our SimPlat, it could be improved by implementing the capability of rotating and moving at the same time. We didn't get to do that. Also, for ground system, we recommend adding a semi-automatic mode, which would allow the user to select the target on the screen, on the camera, and the CubeSat would autonomously navigate towards that target. Another thing we would have liked to add would be adding visuals and dashboards with all of our sensory data for the user to be able to see. And lastly, adding a feature to switch from manual mode to autonomous mode would have made the ground system a lot better as well. So this concludes our presentation. We hope you all enjoyed it. We'll now be taking questions.
Wait. I'll unmute everybody. Unmute all. All right, cool.
Okay, so I'll ask the first question. If no one else wants it.
That's fine. What's up, Russ?
Started off by saying there are over 100 million bits of space junk.
Mm-hmm.
So it doesn't seem feasible to deorbit them all one by one. So,
yeah.
So how does that, that fact relate to this strategy, this deorbiting strategy?
You mean like why, you mean clearing the way for future?
Yeah, you couldn't use, you can't use CubeSat on each individual piece of space junk, when you're talking about 100 million of them.
Yeah, a lot of the space junk was like debris, which isn't very large pieces of space junk. The 128 million bits, only a small amount of that were like larger pieces, which in that case, those would be the ones you would want to deorbit.
So if you deorbit the larger ones, that doesn't solve the problem though, does it? The little ones cause a lot of problems. A BB-sized space junk can kill you.
Hi, Russ. This is Pablo.
Yeah. Hi.
Aerospace. So I can maybe add to that, to their answer. Part of the idea and part of the concept for this was not only space junk, but also to service ailing satellites.
Mm-hmm.
So in that sense, you could potentially try to orbit next to them and with some sort of robotic arm, maybe navigate yourself and service a satellite or send it off into a, if it's, let's say, powered down and it can't deorbit itself, then potentially this thing could send it off into a different orbit.
Okay, so that makes a lot more sense if you think of CubeSat as a kind of repair robot or something like that.
Right, cool. So just a heads up, everybody, we have 3 minutes left, just about.
Hey,
Well, each one of these presentations is allocated an entire hour. So we have like 30 minutes left if you want to use it. We don't have
only
to
allowed,
use it.
Yeah, no, we have only a 40-minute, I guess, non-paid Zoom account.
So if no one has any questions, what I did in the presentation on Monday was let each team member say something about what their experience was and anything else they want to add.
Oh.
What do you think about that?
I guess I'll go first. So, I mean, I enjoyed working on the project, working with the Raspberry Pis and being able to see what they're capable of. I thought it's really neat to kind of see your code actually somewhat coming to life, as opposed to, most of us just see our code just printing out numbers and print statements for the most part. But yeah, this is a little different from what we're normally used to. So all in all, I thought it was a pretty fun project.
Yeah, I had to agree with John. Like, it was fun working with Raspberry Pi, and it was also kind of neat to see the project actually physically move from the code we wrote. And thinking back on the code we wrote now, there are some improvements I would like to add to it and some changes. It's definitely like a good learning experience on like techniques of different techniques I could use for this kind of project.
Yeah, I agree with Jonathan and John. It was cool working with Raspberry Pis and hardware, and also since we're just used to working on like our laptop on one like coding assignment, it was different working with 3 different systems that were intertwined together and integrating them and seeing them all work, I guess, like together was a pretty cool experience.
Yeah, I think my favorite project was probably getting to like, I guess, working on like a large project is probably like what I enjoyed, because most of the projects I've ever worked on were like solo projects or like small projects, mini projects, and this was like one was like a longer deadline. It was like a lot more ambitious than like anything I've ever tried before. And I think there's like there's a lot more people. Like I think getting to meet like aerospace teachers and working like closely with them was like a very interesting experience for me. Getting to like see like industry professionals and people who like been through it like yourself, Russ and Sue and things like that, is like getting to like know and like dip into that pool of information was probably like the most, probably like the thing I'll take the most from this project. It's like the people I met and things like that. Yeah, so that's probably like what I enjoyed the most about this project. Other than that, yeah, it was good. It was interesting.
So, okay, so what did you not enjoy?
The